Before we dive into complex simulations, everything in FEA starts with one foundation, the mesh. A good mesh gives you accurate results. A bad mesh gives misleading results. In today's video, let's understand what meshing really is and why it is considered the heart of finite element analysis. In this series, we will cover meshing in ANSYS from beginner to advanced level. In this first video, we are focusing on the fundamentals, what a mesh is, what it represents, and why it is essential for structural analysis. A mesh is a collection of small elements that divide a model into simple shapes, typically triangles or quadrilaterals in 2D. These elements act like building blocks that allow the FEA solver to approximate the behavior of your structure under loads. Real structures have continuous geometry, infinite points, but a computer cannot solve infinite equations. FEA converts your model into a finite number of elements. Inside each element, equations are solved mathematically and connected through nodes. The process of converting a real continuous domain into small finite pieces is called discretization. The solver approximates the displacement field inside each element using shape functions. In 2D meshing, we commonly use quadrilateral elements, triangular elements, or a combination of both. Each has its own advantages. Quadrilaterals provide higher accuracy, while triangles easily fit complex shapes. A mesh directly affects the accuracy, stability, and convergence of your simulation. A poor quality mesh can produce incorrect stress values or even cause the solver to fail. We will explore mesh quality metrics in detail later, but at a high level, finer mesh, more accuracy. Coarse mesh, faster computation. The key is to balance both. Let's look at a quick demonstration. This is a simple 2D geometry inside ANSYS. Right now, you're looking at the default mesh. Notice the element size, the distribution, and the overall count. This is the starting point before refinement. Now I'll reduce the element size. As I apply the changes, watch how the mesh becomes denser. The elements are smaller, more detailed, and much more numerous. A finer mesh improves accuracy because the solver captures the variations in stress and deformation more precisely. But remember, it also increases computation time and memory usage. This demonstration shows why choosing the right mesh size is so important in FEA. Before running any simulation, you must decide how fine the mesh needs to be for your engineering problem. Fine enough for accuracy, but not unnecessarily heavy. To summarize, a mesh divides your geometry into small finite elements. FEA solves equations on each element to approximate real behavior. And a good quality mesh is essential for accurate and reliable simulation results. Before we close, a quick note. We also provide project and research assistance for students, professionals, and industries. Whether you need help with CFD, FEA, thermal analysis, optimization, dynamic mesh, multiphysics, or advanced simulations in ANSYS, Abacus, Star CCM+, SolidWorks, OpenFOAM, and more, we support academic projects, final year work, MTech PhD research, industrial case studies, and simulation-based consulting. If you need guidance, collaboration, or simulation support, feel free to contact us. Your project success is our priority. And if you found this tutorial helpful, make sure you like, subscribe, and turn on notifications to stay updated with our upcoming tutorials and CFD and FEA videos. Thank you for watching. See you in the next video.